So the first problem we're looking at is 18.1 on worksheet 18. And the first question it asks is, what is the strongest type of intermolecular force in the following compounds? The options it gives us are dipole-dipole interactions, London dispersion forces, or hydrogen bonding. So I've made the following little flowchart here just to direct us a little bit. The first question we're going to ask ourselves, is the molecule polar? First, we have to draw out the Lewis structure, look at what the VSEPR shape would be, and determine from there if it's polar. If the molecule is not polar, then what we're going to be seeing is London dispersion forces. So London dispersion forces will be the strongest force that a non-polar molecule can have. If it's polar, we have to ask ourselves, is there a hydrogen bonded to any of these three atoms? And we ask ourselves this because if there isn't a hydrogen bonded to F, bonded to an O, or bonded to an N, so if this doesn't occur, then what we have is only dipole-dipole interactions. So dipole-dipole interactions are for polar molecules with no bonds. If there is an HF, HO, or HN, then we can have hydrogen bonding. So using this flowchart, we can go ahead and answer all of these questions. Starting with methanol, let's figure out what the strongest intermolecular force is. So if we were to draw it out, if we show that bent geometry, then we see methanol right there. So speaking just in terms of polarity, this is a polar molecule, and we see that there is a partial negative charge on the oxygen and a partial positive charge on that hydrogen. So if we look back at our flowchart, we'll see that it is a polar molecule and that there's also an oxygen bound to this hydrogen. And so it's polar. There is an OH bond. And so I'm going to classify this one as hydrogen bonding as its strongest intermolecular force. So moving on to the next one, we have PF3. If we draw out this structure, we see that it has a shape that is trigonal pyramidal. So if we were to look at the overall polarities of each bond, we know that fluorine is very electronegative. So we'll be seeing most of the electron density pulled towards the fluorines and away from the phosphorus in the middle. If we look at the overall polarity of the molecule as a whole, there's a net dipole moment going towards the fluorine and leaving the phosphorus in the middle partially positive, and each of these fluorines as partially negative. So we see that this is a polar molecule, and now we have to ask ourselves if there are any HFON bonds. All we have here are FP bonds. There aren't even any hydrogens. That means that we can classify this as a polar molecule with no H bonding. And so the strongest intermolecular force we have is dipole-dipole interactions. Moving on to XeF4, if we're to draw that out, the overall shape of this is going to be square planar. So square planar, bound to 4 of the same atoms, this is a non-polar molecule. So even though there's electron density being pulled toward the fluorine, what we see is that it's being pulled in 4 different directions, and there is no overall dipole moment, it just cancels out. Since this is a non-polar molecule, the only intermolecular force that's available for non-polar molecules is London dispersion forces. Moving on to the next one, we're looking at N2. So N2 is a diatomic molecule. This is its Lewis structure. This is a completely covalent bond, and it is non-polar. Any diatomic element is a non-polar molecule, and therefore the only intermolecular force it has, again, is London dispersion forces. Moving on to the next one, SO2. If we were to draw the Lewis structure of SO2, there's a resonance structure, but I'll just draw one of them. We notice its bent shape. You know that things that are bent, they have that lone pair there. This is typically a polar molecular shape. We know it's polar, so we have to ask ourselves, is there any HF, HO, or HN bonds? Well, there's not even any hydrogens here, and so that's a no to all of those things. And so this is just a polar molecule with no hydrogen bonding. That means that the intermolecular force is just dipole-dipole interactions. So we're looking at HBr now. So if we were to draw out the Lewis structure for this, we would see H bound to a Br does have a pretty strong dipole moment pointing towards the bromine. So the bromine will be partially negative then the hydrogen will be partially positive. This is a polar molecule. We have to ask ourselves, whenever we see we have a polar molecule, is there some sort of H-bond? And we see no, that the only H bond we have in here is to a bromine. So we have an HBr bond, but that is not enough to give us hydrogen bonding. Is just dipole-dipole interactions as its strongest intermolecular force.